All right, lesson 8, all about the energetics of hydration. So let's start talking about enthalpy of solution. So the enthalpy change of solution is the enthalpy change when 1 mole of a solute is dissolved in a solvent to infinite dilution under standard conditions of temperature and pressure. Ionic compounds generally dissolve in the polar solvent water. Okay, so if you take a solid ionic compound and you dissolve it, what is the amount of energy that is either released or absorbed? That's what we're going to be looking at. So, what exactly happens when an ionic compound dissolves in a solvent? We're going to use water as an example. So, when a compound dissolves in a solvent, this is called solvation. Okay? We're specifically going to look at water as our solvent. And there's going to be a picture on the next slide that you're going to be able to see all of these individual components. Okay, so you're going to see in letter A that the ionic lattice is broken up by polar water molecules. At the contact surface, partial charges in the water molecules are attracted to ions of opposite charge in the lattice, which may cause them to dislodge from their positions. In B, you'll see the partially negative oxygen atoms in the polar water molecules are attracted to the positive ions, and then in letter C, you'll see the partially positive hydrogen atoms in the polar water molecules are attracted to the negative ions. So this is something we've seen before, but we're just going to review that if we have our solid lattice with our ionic compound surrounded by water molecules, okay, the partially polar oxygen is going to be attracted to the positive cation, and the partially positive hydrogen ions are going to be attracted to the negative anion. And because of this attraction, they may dislodge those ions, and that solid ionic compound, the lattice structure, will break apart. So ions separated from the lattice in this way become surrounded by water molecules and are said to be hydrated. So specifically when water is involved and those water molecules surround the ions that are dislodged, this is our hydration. Okay? The strength of interaction between the polar water molecules and the separated ions is given by their hydration enthalpy. So there's some sort of attraction between the ions and the polar water molecules, and this is the enthalpy of hydration, or hydration enthalpy. So the enthalpy change of hydration, the definition of an ion, is the enthalpy change that occurs when 1 mole of gaseous ions is dissolved to form an infinitely dilute solution of 1 mole of aqueous ions under standard conditions of temperature and pressure. Okay, so we can now see how we're going to take the solid ionic compound, break it into its gaseous ions. Okay, hopefully you remember what that is. We learned about that in lesson 6 with the Born-Haber cycle, and then you studied it a little bit more in lesson 7. And then once it is dissolved in water, they become aqueous. So it is very difficult to determine the hydration of individual ions, because when you dissolve an ionic compound, both positive and negative ions are present. Right? When we dissolve an ionic compound, they break up into 2 ions. So we resolve this by measuring the enthalpy of hydration of the hydrogen ions separately using an indirect spectral technique. Okay, so converting the gaseous hydrogen ion into an aqueous hydrogen ion gives us an enthalpy change of hydration of negative 1,130 kilojoules per mole. So with this as our reference, we can then measure the energy absorbed or released with other ions with hydrogen to calculate their enthalpy of hydration for individual ions. Okay, so here we can see what an equation would look like if you were to be asked to identify it. So the enthalpy change of hydration of an ion is the enthalpy change that occurs when 1 mole of gaseous ions is dissolved to form an infinitely dilute solution of 1 mole of aqueous ions. So we do that for the cation, which we can see first because it is positive, and then we do it for our anions. So there's 2 hydration enthalpies that we have to take into account. So as there is a force of attraction between the ions and the polar water molecules, it is an exothermic process and the enthalpy changes are negative. Okay, so as you'll see, all of the enthalpy changes for ions specifically are negative. They are exothermic. This information is given in the data booklet. Okay, we can look at some trends. All right, we can compare down a group. So as we go down group 1 with our alkali metals, we can see that they are decreasing, meaning they become less exothermic. And then we also see that with our group 17 halogens. As we go down, they are becoming less exothermic, less negative. And one of the reasons is because the ionic radius is getting bigger. The ionic radius increases. So as that radius increases, the electrostatic attraction between the ions and those polar water molecule decreases. So the farther apart they are, less of an electrostatic attraction, less exothermic, less energy is going to be released. Whereas if they are smaller and closer to the water molecule, there's a stronger attraction and more energy would be involved. So here is a mathematical relationship. You do not have to memorize this, but this just shows you how when you decrease the size of the radius, you increase the enthalpy of hydration. So it's an inverse relationship. One other thing we can look at is the trend across period 3. So before we were looking at the group and the size, but let's say we move left to right across period 3 and look at the enthalpy of hydration for metals. Well, they become more exothermic for 2 reasons. The ionic charge increases and the ionic radius decreases. So this is very, very similar to what we saw with the relationship between charge and radius with lattice enthalpies. So both of these changes lead to an increased attraction between the positive ion and the partially negative charged oxygen atoms in the water molecules. So again, we're looking specifically at the metal, the cations. So here is the relationship in equation form that, again, you do not have to memorize, but it's just showing you where as you increase the charge, so let's say we go from a sodium +1 to a magnesium +2, aluminum +3, they are also getting smaller, so increasing in charge and getting smaller, and you can see how the hydration enthalpy is getting much, much more exothermic. Okay, here are some graphs that show you those relationships that we have been talking about. So now we're going to bring in that lattice enthalpy that we were discussing in the previous lessons. And how do we take the hydration enthalpy to calculate our enthalpy of solution? So the solution of a substance can be understood by imagining that the solid is first sublimed into gaseous ions, which are then plunged into water. Okay, so I'm going to talk about the equation here, and then how we're going to interpret a version, I guess you could call it, of it's very similar to a Born-Haber cycle, but it's going to involve a different process. Okay, but it is a different energy cycle that we're going to look at. So, to calculate the enthalpy of solution for a solid compound, you're going to add the lattice enthalpy to the hydration enthalpy of your cation and then you're going to add the hydration enthalpy of your anion. So this is an equation that you should learn. It is not in the data booklet. So let's look at our energy cycle here below. Okay, we're going to start down in the corner with the sodium chloride. Okay, it is solid. So we can first imagine that we take that solid and we turn those solid ionic compound into gaseous ions. Okay, well, as we can see, the arrow is going up, and that is an endothermic process because that is our lattice enthalpy. That is the definition, taking a solid ionic compound and bringing it into its gaseous ions. Well, those gaseous ions, as we can see in the upper left, are then plunged into water and they become aqueous. That is our hydration enthalpies. Those are the two values on the right-hand side. They are both negative, so that's an exothermic process, so we see our arrow going down. Okay? Well, if we were to take the solid sodium chloride and just put it in water, it would turn into those aqueous ions. So this is our enthalpy of solution in the bottom right. This is the unknown that we need to solve for. So we take the lattice enthalpy, which is 790. We add it to our enthalpy of hydration for our cation, which is negative 424, and add it to our enthalpy of hydration for our anion, which is negative 359, which we see here. 790 minus 424 minus 359. And when we do all that, that gets us to about positive 7 kilojoules per mole, which means that when you take solid salt, solid sodium chloride, dissolve it in water, 7 kilojoules per mole is absorbed. Okay, which means the temperature would slightly decrease when you dissolve. Okay, very, very small. This is a very small amount. There are bigger ones that you are going to see. Okay, so this is a cycle that you could be asked to draw or identify. If you just remember to add the lattice enthalpy to the two hydration enthalpies, you will get an answer. It's not always positive. It can be negative. Okay, why don't we look at just a few practice problems to wrap this lesson up. Number 52 says, discuss the relative enthalpies of hydration of the sodium ion and the fluoride ions. Okay, so I went ahead and looked at the table from the previous slide. You could have also looked at your data booklet. The sodium ion is negative 424. And the fluoride ion is negative 504. Okay, so discuss these in relation to ionic radius. Okay, well, the sodium ion and the fluoride ion have about the same radius. Okay. Okay, they have the same radius. So you would think that because they have the same size, the charges are the same number, that they would have, a similar enthalpy of hydration. But as we can see, that's not true. Right? The fluoride ion has a little more exothermic value. But we can see that there has to be another reason. And that reason, if you remember, is the fluoride ion can form hydrogen bonds. Right? There is a stronger attraction between the fluoride ion and the water than there is the sodium ion and the water. So because there's a stronger attraction, there's a little bit more energy involved with the enthalpy of hydration, in this case for the fluoride ion. Okay, why don't we try number 53, where we're going to use an energy cycle to calculate the enthalpy of solution of potassium chloride from data in sections 18 and 20 in the IB data booklet, And then we're going to, in letter B, calculate the percentage inaccuracy of your value by comparing with the value in section 19 and comment on the disagreement between the two values. Okay, so you're going to need your data booklet. Section 18 is all about lattice enthalpy, and section 20 is going to be your hydration enthalpies. And then section 19 is all about the enthalpies of solution. Okay, so we specifically want to calculate the enthalpy of solution of potassium chloride. So we're taking solid potassium chloride and we're going to dissolve it in water, meaning we're going to take that solid and turn it aqueous. Okay, that's what we're going to do, but we have to remember that we're first going to turn those ions into gas. Okay, so that solid ionic compound is going to turn into our gaseous ions. Okay. Also remember that this potassium chloride that is aqueous, okay, technically I shouldn't have written it like that. I should have written it as potassium that is aqueous and chloride that is aqueous, because they dissolve into their aqueous ions. Okay, well then we take this gaseous ions, plunge them in water, and turn them into aqueous. So this first step, okay, going up, that is our lattice enthalpy. Okay, you should find that in section 18. This arrow in the upper right, that is our enthalpy of hydration. Okay, HYD for hydration. And then this arrow here, that is our enthalpy of solution, delta HSOL. Okay, so all you have to remember is to take the lattice enthalpy and add the two hydration enthalpies. So when you do that, you would look up that the lattice enthalpy is about 720. The hydration enthalpy for potassium ion is negative 340. And then the negative 359 is for the hydration enthalpy of the chloride. So when you add that, you get positive 21 kilojoules per mole. So again, a slightly endothermic process that occurs when you take solid potassium chloride and dissolve it in water. If we were to then look up the value in the data booklet for potassium chloride, you would see that it's about positive 17.22. So you do our percent error to try and see how accurate we are, and we'll see that the large inaccuracy, which is about 22%, is based on the calculated value being different, because we're finding the difference between two pretty large values.